A rocket does not fail slowly. It ends in an instant. One moment, a column of fire carves a path through the atmosphere, engines roaring with the controlled violence of physics itself. The next, everything collapses into chaos. Pressure breaks symmetry. Fuel and oxygen, once perfectly balanced, turn against each other. Metal folds, turbo pumps overspin. A shockwave blooms brighter than the sun for a fraction of a second, and billions of dollars dissolve and into incandescent fragments. This is not drama. This is thermodynamics. A modern orbital rocket is a controlled explosion held together by precision so unforgiving that a deviation smaller than a human hair can cascade into total destruction. Inside its tanks, cryogenic propellants sit at temperatures colder than deep space. Liquid oxygen waits, dense and volatile. Liquid methane or hydrogen, restless with energy, demands containment at the edge of possibility. Between them, thin walls. Between success and failure, equations that leave no room for mercy. Now imagine the scale. A vehicle designed to push beyond Earth's gravity carries not just mass, but ambition. Years of engineering, thousands of minds, supply chains that stretch across continents. Every bolt, every weld, every line of code aligned toward a single moment. Ignition. The engines light. Combustion chambers reach temperatures hotter than the surface of the sun. Exhaust plumes expand into the lower atmosphere, generating thrust that must exceed the weight of the entire vehicle by a precise margin. Too little, and it never leaves the ground. Too much, and structural loads tear it apart. There is no forgiveness in ascent. Max Q arrives, the point where aerodynamic pressure peaks. The air itself becomes a force that tries to rip the rocket sideways. Guidance systems adjust by milliseconds. Actuators strain. The structure flexes just enough to survive, but never enough to yield. If anything is misaligned, even slightly, the consequences are immediate. A tiny leak in a fuel line becomes a jet of supercooled fluid, freezing nearby components. A sensor glitch feeds incorrect data to the flight computer. The engine mixture ratio drifts outside its narrow window. Combustion becomes unstable. Vibrations amplify. Resonance builds. Metal fatigues under stresses it was never meant to endure. Then the chain reaction begins. A rupture, a flash, a sphere of expanding gas, moving faster than thought. In less than a second, the vehicle ceases to exist as a coherent object. It becomes a cloud of debris, each fragment carrying the momentum of failure outward in all directions. The sky briefly holds the memory of what was meant to be a path to orbit. This is the true cost of reaching space. Not just money, though the numbers are staggering. A single launch vehicle can represent investments exceeding $10 billion when development, infrastructure, and operations are counted together. Not just time, measured in decades of iteration and risk, but the confrontation with a universe that does not care about intention. Gravity does not negotiate. Pressure does not forgive. Energy does not hesitate. In the silent vacuum beyond the atmosphere, there is no sound, no resistance, no second chances. But it is here, in the thick lower layers of air, in the violent transition from Earth to space, that the dream is most fragile. Because to leave this planet, you must pass through a narrow corridor where everything is trying to stop you. And if, for even a moment, the balance is lost, everything is lost with it. What appears to the human eye as a single explosion is, in truth, the final expression of a system that was always on the edge of impossibility. To understand how a $15 billion machine can vanish in seconds, you have to descend into the anatomy of a rocket, where every component exists in a state of negotiated survival. A launch vehicle is not a machine in the traditional sense. It is a temporary structure designed to endure forces it was never meant to tolerate for long. Unlike an airplane, which is built for repetition and endurance, a rocket is built for a single act of defiance. It is assembled with the knowledge that it will either succeed completely or fail catastrophically. There is no middle ground. At its core, propulsion is driven by one of the most fundamental principles in physics. For every action, there is an equal and opposite reaction. But the simplicity of that statement hides an almost absurd level of complexity. Inside the engine, fuel and oxidizer are injected into a combustion chamber at pressures so extreme that the molecules themselves are forced into violent interaction. The chemical bonds break and reform in fractions of a millisecond, releasing energy that has been stored since the formation of those atoms in ancient stars. The flame that emerges is not just fire. It is history, collapsing into heat. Temperatures climb beyond 3,000 degrees Celsius. Metals that would melt instantly under normal conditions are kept intact only by active cooling systems, where the fuel itself is circulated through the engine walls before being burned. The structure survives by flirting constantly with its own destruction. And then there are the turbo pumps. These machines spin at tens of thousands of revolutions per minute, pushing cryogenic fluids with such force that any imbalance becomes lethal. A turbo pump is less forgiving than a heartbeat. If it falters, even briefly, the flow of propellant becomes uneven. Pressure oscillates. Combustion destabilizes. It is like forcing a symphony to continue after removing a single instrument, only to realize that the missing note was the one holding everything together. The precision required is almost philosophical in nature. It raises a question that echoes far beyond engineering. How much imperfection can reality tolerate before it collapses into chaos? Because a rocket is, in many ways, a physical answer to that question. The margins are microscopic. A valve opening a fraction of a second too early can flood a chamber. A sensor reading a slightly incorrect temperature can trigger a cascade of incorrect decisions. The flight computer, executing thousands of calculations per second, must interpret a storm of data and respond with absolute accuracy. There is no intuition, only logic executed at a speed that leaves no room for doubt. And yet, uncertainty is everywhere. The atmosphere itself is not a uniform medium. It shifts, breathes, and moves in invisible currents. As the rocket ascends, it encounters layers of varying density, temperature gradients, and wind shear. These forces are not constant. They are alive in a statistical sense, governed by probabilities rather than certainties. Max Q, the moment of maximum aerodynamic pressure, represents a convergence of speed and atmospheric density. It is the point where the rocket experiences the greatest external stress. The air resists, compresses, and pushes back with invisible hands. The structure must endure bending forces that try to snap it in half. Imagine holding a thin metal rod and pushing it to its limit, feeling the subtle trembling just before it buckles. Now imagine that rod is over 70 meters tall, accelerating upward at supersonic speed, carrying tanks of explosive energy. This is where failure often finds its opportunity, because nature does not need a large opening to impose its will. It only needs a weakness. Consider the behavior of fluids under extreme conditions. Liquid oxygen, at temperatures near -180 degrees Celsius, is dense and reactive. It feeds combustion with ruthless efficiency. Liquid hydrogen, even colder, is so light that it escapes through imperfections almost invisible to the eye. These substances are not passive. They are constantly interacting with their environment, expanding, contracting, and seeking equilibrium. Containment is an illusion maintained by engineering. A microscopic crack can become a pathway. A seal can degrade under thermal stress. As the rocket climbs, temperatures change rapidly. The outside skin heats from atmospheric friction, while the inside remains cryogenically cold. This creates gradients that induce stress within the material itself. Expansion and contraction occur simultaneously in different regions, pulling the structure in opposing directions. It is a silent tug of war at the molecular level. And then there is vibration. Combustion is not always smooth. It can oscillate, creating pressure waves that travel through the engine and into the structure. These oscillations, if they align with the natural frequencies of the rocket, can amplify into resonance. The entire vehicle begins to shake, not visibly at first, but internally, where bolts loosen and materials fatigue. This phenomenon, known as combustion instability, has destroyed rockets that were otherwise perfectly designed. It is a reminder that even in a system governed by precise equations, emergent behavior can arise. Complexity breeds unpredictability, and unpredictability in an environment this extreme is indistinguishable from danger. Now expand this understanding beyond the machine itself. A rocket is a convergence point of human intention and cosmic law. It is where ambition meets the uncompromising structure of the universe. Every calculation, every simulation, every test is an attempt to predict a reality that does not reveal itself fully until the moment of launch. There is something deeply humbling in that. Because despite all knowledge, all preparation, the final outcome is still determined in real time, under conditions that cannot be perfectly replicated. The launch is not just a technical event. It is an encounter with the limits of control. And when failure happens, it is absolute. There is no gradual decline, no partial success that can be salvaged. The energy contained within the propellants is released almost instantaneously. Chemical potential becomes kinetic violence. The structure, once rigid and purposeful, disintegrates into fragments that follow trajectories dictated by the same laws that once held them together. In that moment, the rocket becomes a lesson, a demonstration of how thin the boundary is between order and chaos. Billions of dollars, years of effort, and the combined expertise of countless individuals are undone in less time than it takes to blink. Not because of negligence or ignorance, but because the system itself operates at the edge of what is physically possible. And this is the paradox. To reach space, humanity must build machines that exist in a state of controlled instability. Success depends on maintaining that instability just long enough to escape Earth's gravity. Failure occurs when that balance is lost, even briefly. It is like trying to balance a needle on its tip while a storm rages around you. The fact that it works at all is extraordinary. The fact that it sometimes does not is inevitable, because the universe does not reward effort. It only responds to precision. And precision at this scale is not just difficult, it is fragile. Failure in rocketry is never a single event. It is a sequence, a hidden narrative written in pressure curves, temperature gradients, and microsecond decisions. Long before the visible explosion, the outcome is already unfolding, buried deep inside the system, where no human eye can follow in real time. Telemetry becomes the only witness. Thousands of data points stream down every second. Chamber pressure, turbo pump speed, structural loads, vibration frequencies, guidance vectors. Each number is a fragment of truth, a pulse in a digital heartbeat that describes the health of the vehicle. To an untrained observer, it is noise. To those who understand it, it is a language. And sometimes, that language begins to whisper. A pressure reading drifts slightly above nominal. Not enough to trigger an abort, not enough to stand out in isolation, but enough to suggest that something is changing. A temperature sensor reports a value that is technically within limits, yet subtly inconsistent with the surrounding data. A vibration frequency appears, faint at first, like a distant echo. Individually, these signals are harmless. Together, they form a pattern. In complex systems, failure rarely announces itself clearly. It emerges from correlation. Small deviations align, reinforcing one another, until the system crosses a threshold. This is how order dissolves. Not through a single catastrophic cause, but through the accumulation of minor imperfections that synchronize at the worst possible moment. It is the physics of tipping points. Inside the engine, combustion instability can begin as a barely detectable oscillation. Pressure waves reflect within the chamber, bouncing between injector plate and nozzle, interacting with the flow of propellants. Under the right conditions, these waves amplify. The chamber becomes an acoustic cavity, resonating with energy that was never meant to exist. The result is not just noise, it is force. Each oscillation exerts stress on the chamber walls, on the injectors, on the entire structure. The metal experiences rapid cycles of compression and expansion, far beyond what steady-state calculations predict. Microscopic fractures begin to form. They are invisible, but they are real. And once a crack exists, it does not remain small. Material science reveals a quiet truth. Under repeated stress, flaws grow. A crack concentrates stress at its tip, making it easier for the next bond to break. This process accelerates. What begins as a defect measured in micrometers can expand to catastrophic proportions in milliseconds. This is how integrity fails. Now consider the flow of propellants. The mixture ratio between fuel and oxidizer must remain within a narrow band. Too much oxidizer, and the combustion becomes excessively hot, eroding the chamber. Too much fuel and efficiency drops, altering thrust and destabilizing the trajectory. Maintaining this balance requires perfect synchronization between valves, pumps, and control algorithms. But perfection is theoretical. In reality, delays exist. Signals take time to propagate. Valves have mechanical inertia. Fluids do not respond instantly. They surge, they cavitate, they form vortices. Under certain conditions, the flow can separate, creating pockets where pressure drops suddenly, leading to vapor formation inside the liquid stream. This phenomenon, known as cavitation, is particularly destructive. When vapor bubbles collapse, they generate localized shock waves strong enough to damage metal surfaces. Inside a turbopump spinning at extreme speed, cavitation is like sandblasting the interior with microscopic explosions. Over time, this degrades performance. In a critical moment, it can trigger failure. And yet, all of this is happening while the rocket is accelerating faster and faster. Guidance systems must continuously adjust the vehicle's orientation. Small gimbals tilt the engines, redirecting thrust to maintain the intended trajectory. These adjustments are calculated based on inertial measurements, gyroscopes detecting rotation, accelerometers measuring changes in velocity. But sensors are not perfect observers. They are subject to noise, drift, and bias. A gyroscope may report a rotation that does not exist. An accelerometer may misinterpret vibration as acceleration. The flight computer must filter this data, distinguishing signal from noise, reality from artifact. This process is an act of interpretation. An interpretation introduces the possibility of error. If the guidance system believes the rocket is tilting when it is not, it may command a correction that creates the very deviation it was trying to prevent. A feedback loop forms. The system begins to chase its own misperception, amplifying instability instead of suppressing it. This is how control becomes loss of control. The philosophical implication is unavoidable. A system designed to maintain order can, under certain conditions, become the source of its own collapse. The same intelligence that guides the rocket can misguide it. The same precision that enables flight can magnify error. There is no clear boundary between success and failure, only a continuum. As the rocket climbs higher, the atmosphere thins. Aerodynamic forces decrease, but velocity increases. The vehicle approaches orbital speed, a horizontal velocity of nearly 8 kilometers per second. At this speed, energy scales dramatically. Kinetic energy grows with the square of velocity, meaning small increases in speed result in disproportionately large increases in energy. The system becomes more energetic, more sensitive, more unforgiving. A structural failure at this stage is not just a break. It is a release. Energy stored in motion, in pressure, in chemical bonds, is liberated all at once. The vehicle disintegrates, and each fragment carries a portion of that energy forward. Debris spreads along trajectories determined by the final state of the system, tracing invisible arcs through the sky. From the ground, it appears as a sudden bloom, a brief, violent flower of light. But within that moment is the culmination of countless interactions, each governed by physical laws that are indifferent to intention. And this indifference is the most profound aspect of all. The universe does not recognize ambition. It does not assign value to effort or cost. Whether a rocket represents $1 billion or a decade of human life, the outcome is determined solely by the alignment of conditions. If the equations balance, the rocket reaches orbit. If they do not, it falls apart. There is no negotiation. This realization extends beyond rocketry. It speaks to the nature of complex systems everywhere. Whether in engineering, biology, or even human societies, stability is often an emergent property, maintained through delicate interactions. When those interactions shift, even slightly, the system can reorganize into a completely different state. Order becomes chaos, and chaos, in turn, follows its own form of order. In the aftermath of a rocket failure, investigators reconstruct this hidden narrative. They analyze telemetry, examine debris, simulate conditions, searching for the origin of the cascade. They are not just looking for a broken component. They are searching for the moment when possibility narrowed into inevitability, because somewhere, within milliseconds, the system crossed a line, a point of no return. And once that line is crossed, no command, no correction, no human intervention can reverse it. The processes unfold at speeds beyond reaction. The outcome becomes locked in, dictated by the momentum of physics itself. This is the true meaning of irreversible failure. Not simply that something broke, but that it reached a state from which recovery was no longer physically possible. And in that sense, Every launch carries within it a silent question. Not whether failure is possible, but when and under what conditions the universe will decide that the balance has been lost. Beyond the violence of a single failure lies a deeper reality, one that stretches far beyond any individual rocket, any company, any moment of loss. To understand what is truly at stake, you have to shift perspective from the machine to the environment it is trying to escape. Earth is not simply a planet. It is a gravitational well, a curvature in space-time so deep that escaping it requires an almost absurd expenditure of energy. Every object on its surface is held in place by an invisible geometry, a constant pull toward the center that never rests, never weakens, never negotiates. To leave this well, a rocket must reach what is known as escape velocity, approximately 11 kilometers per second. This is not just speed, it is liberation from a curvature that defines existence itself on this world. But rockets do not leap directly to escape velocity. They climb. They build energy gradually, converting chemical potential into motion, step by step, second by second. Each stage of flight is a careful negotiation with gravity, trading fuel mass for velocity. The rocket becomes lighter as it burns propellant, shedding weight to gain speed, like a creature discarding parts of itself to move faster. This is why rockets are staged. Lower stages, massive and powerful, operate in the dense atmosphere, where drag is significant and thrust must be immense. Once their fuel is spent, they are discarded, falling back to Earth, no longer useful. Upper stages continue the journey, operating in thinner air, where efficiency becomes more important than raw force. It is a process of sacrifice. Each stage exists only to enable the next. None of them are meant to survive the full journey. Even in success, destruction is part of the design. There is something profoundly philosophical in this architecture. Progress, in this context, is inseparable from loss. Now consider the energy involved. The energy required to place a payload into orbit is comparable to the explosive power of hundreds of tons of TNT. This energy is not released all at once, but it is present, contained within the propellants, waiting to be converted into motion. The rocket carries within it the potential for both creation and destruction. This duality is unavoidable. The same energy that can place a satellite into orbit, enabling global communication and observation, can also, if uncontrolled, tear the vehicle apart in an instant. The difference lies not in the energy itself, but in how precisely it is managed. Control is everything, and yet control is always incomplete. Because the rocket does not travel through empty space alone. It moves through an environment that changes continuously, from the dense lower atmosphere to the near vacuum of space, from subsonic speeds to hypersonic regimes where the very air behaves differently. At hypersonic velocities, above 5 times the speed of sound, the air cannot move out of the way quickly enough. It compresses violently, forming shock waves that wrap around the vehicle. Temperature rises dramatically. The air itself begins to dissociate, molecules breaking apart under the stress, creating a plasma-like sheath around the rocket. In this regime, the boundary between object and environment becomes blurred. The rocket is no longer just moving through the air. It is transforming it. This transformation introduces new uncertainties. Shock waves can interact with the structure in complex ways, reflecting and interfering, creating localized monadic of intense pressure. Heat transfer becomes uneven. Some ajza of the vehicle experience extreme temperatures, while others remain relatively cool. These gradients induce stress, warping materials, challenging their limits. Even the shape of the rocket, carefully designed through computational simulations and wind tunnel tests, becomes a variable in real conditions. Small imperfections, surface roughness, slight deviations from ideal geometry can alter the flow in ways that are difficult to predict. This is the nature of fluid dynamics at extreme conditions. It is deterministic in principle, governed by equations, yet chaotic in practice, sensitive to initial conditions in ways that defy perfect prediction. This sensitivity echoes a broader truth about complex systems. Small causes can produce large effects. A tiny perturbation in airflow can shift pressure distribution. That shift can alter structural loading. That loading can exacerbate a weakness. That weakness can lead to failure. The chain is unbroken. Now extend this perspective further outwards, beyond the atmosphere, into orbit. Reaching orbit is not simply about going up. It is about going sideways fast enough that as the rocket falls toward Earth, the planet curves away beneath it. Orbit is a state of perpetual falling, where forward motion continuously misses the ground. This delicate balance between gravity and velocity defines everything in orbital mechanics. Too slow, and the vehicle falls back to Earth. Too fast, and it escapes into deep space. Too imprecise, and the orbit becomes unstable, decaying over time or intersecting with the atmosphere. Precision is not just required for launch, but for insertion into orbit itself. And here, another layer of complexity emerges. Timing. The Earth rotates. Launch windows are constrained by the desired orbital plane. A delay of seconds can alter the trajectory. Guidance systems must account for the rotation of the planet, the curvature of space, and the gravitational influence of other bodies. Even the moon, distant and silent, exerts a measurable pull. The rocket operates within a gravitational landscape that is dynamic, multi-layered, and interconnected. Failure to account for any of these factors can result in a trajectory that deviates just enough to become unsustainable. And once again, the margins are small. A deviation of a fraction of a degree can translate into hundreds of kilometers over time. An error in velocity of just a few meters per second can determine whether a payload remains in orbit or re-enters the atmosphere. This is the scale at which success and failure are defined, not in broad strokes, but in fine details. Now return to the moment of explosion. When a rocket fails, it does not simply lose its mission. It releases its energy back into the environment, abruptly and uncontrollably. The carefully managed conversion of chemical energy into directed motion becomes a chaotic expansion of heat, light, and kinetic fragments. The system transitions from order to entropy. Entropy, in thermodynamic terms, is a measure of disorder, of the number of ways a system can be arranged. A functioning rocket represents a highly ordered state, where energy flows are constrained and directed. An explosion represents a rapid increase in entropy, where energy disperses and the number of possible configurations increases dramatically. This transition is irreversible. Once the energy has been released, once the structure has disintegrated, there is no path back to the original state. The rocket cannot be reassembled from the expanding cloud of debris. Time itself, in a thermodynamic sense, has moved forward. And this brings us to a deeper implication. Every launch is an attempt to temporarily reverse the natural tendency toward disorder. Fuel is refined, components are manufactured with precision, systems are assembled into a coherent whole. Energy is stored, organized, prepared. The rocket is a localized decrease in entropy, a pocket of order created through human effort. But maintaining that order requires constant input. The moment control is lost, the system relaxes back toward disorder, releasing its stored energy in the process. This is not failure as an anomaly. It is failure as a return to equilibrium. In this light, the destruction of a rocket is not just a technical event. It is a thermodynamic inevitability expressed under specific conditions. The universe favors dispersion, randomness, equilibrium. Order exists only where it is actively sustained. And spaceflight, perhaps more than any other human endeavor, exists in direct opposition to that tendency. It is an act of sustained defiance against entropy, against gravity, against the natural state of things. Which is why the cost of failure is so high. Not just in money, though the figures are staggering. Not just in time, though years can vanish in a single moment. But in the recognition that the boundary between success and failure is defined by forces that are fundamentally indifferent to human intention. A rocket does not care how much it cost. The atmosphere does not care how many people worked on it. Gravity does not care how important the mission is. The laws of physics remain unchanged. And in that unchanging framework, every launch becomes a question posed to the universe. Can this fragile structure, built by finite minds, withstand the infinite consistency of physical law? Sometimes the answer is yes, and humanity reaches a little farther. Sometimes the answer is no, and everything falls apart, exactly as the equations allow. There is a moment after every catastrophic failure when the sky returns to silence. The fire dissipates. The fragments fall beyond sight. The shock wave fades into the atmosphere, leaving behind an emptiness that feels almost unnatural. What remains is not just the absence of the rocket, but the presence of a question. What exactly was lost? $15 billion is a number that seems to capture the scale, but it is only a surface measurement. Money, in this context, is a compressed form of effort, time, and human intention. It represents factories that operated for years, supply chains that moved materials across oceans, engineers who translated abstract equations into physical reality, and countless iterations where failure was studied, understood, and refined into progress. But even that is incomplete, because a rocket is not just an object. It is a convergence of disciplines that rarely meet at such intensity. Thermodynamics, fluid mechanics, materials science, control theory, orbital mechanics, and computational modeling all intersect within a single structure that must function perfectly for a brief window of time. It is a temporary alignment of knowledge, and when it fails, that alignment collapses. Yet failure is not the end of the story. It is, paradoxically, one of the most valuable forms of data. Every fragment that falls back to Earth carries information. The deformation of metal reveals stress patterns. Burn marks indicate temperature distributions. The condition of components tells a story about the sequence of events. Investigators reconstruct the timeline, not unlike astronomers reconstructing the life of a star from the light it emitted millions of years ago. The debris field becomes a map of causality. Telemetry fills in the invisible parts. Data streams are analyzed frame by frame, millisecond by millisecond. Engineers look for the first deviation, the earliest sign that the system began to diverge from its intended behavior. They search for the origin, the nukt where possibility narrowed into inevitability. And in doing so, they confront a fundamental truth. Failure is rarely caused by a single mistake. It is usually the result of multiple factors interacting in ways that were not fully anticipated. A design margin that was sufficient under one set of conditions becomes insufficient under another. A component that performed flawlessly in testing behaves differently in the integrated system. Assumptions that seemed reasonable prove incomplete. This is the nature of complex engineering. It is not enough to understand each part in isolation. One must understand the interactions, the emergent behavior that arises when everything operates together under extreme conditions. And even then, uncertainty remains. Because no test can perfectly replicate the reality of launch. Ground tests are constrained by gravity, by infrastructure, by safety considerations. Simulations, no matter how advanced, rely on models that approximate reality. There is always a gap between prediction and experience. That gap is where failure lives. But it is also where learning occurs. Each failure reduces uncertainty. It reveals aspects of the system that were previously hidden. It forces a revision of models, an adjustment of assumptions, an expansion of understanding. In this sense, failure is not just a setback. It is a transformation of ignorance into knowledge. The cost is high, but the value of what is learned can exceed the value of what was lost. This creates a tension that is difficult to reconcile. On one hand, the destruction of a multi-billion-dollar rocket appears as a catastrophic waste. On the other, it is part of a process that has, over decades, enabled humanity to place satellites around Earth, send probes to distant planets, and observe the universe with unprecedented clarity. Progress in spaceflight has never been linear. It has been punctuated by explosions, each one a reminder of the limits, and each one a step toward pushing those limits further. There is an analogy here with evolution. In biological systems, countless variations are tested against the environment. Most do not survive. But the information encoded in those failures shapes future adaptations. Over time, complexity increases, not because failure is avoided, but because it is integrated into the process. Rocket engineering follows a similar pattern. Designs evolve, materials improve, control systems become more sophisticated, redundancies are introduced, margins are adjusted. Each iteration carries forward the lessons of previous failures, embedding them into the next attempt. And yet, the possibility of failure never disappears. Because as capability increases, so does ambition. More powerful engines, larger payloads, more complex missions. Each advancement pushes the system closer to the boundaries of what is physically achievable. And at those boundaries, uncertainty grows. It is a perpetual cycle. Success enables greater risk. Greater risk increases the potential for failure. Failure drives deeper understanding. Understanding enables new forms of success. This cycle is not unique to rocketry. It reflects a broader pattern in human exploration. From the first attempts to cross oceans to the development of modern technology, progress has often been built on the remnants of what did not work. The difference in spaceflight is the scale and immediacy of the consequences. When a ship sinks, it disappears beneath the surface. When a rocket fails, it announces itself in fire. The visibility of that failure shapes perception. It creates a sense of finality, of absolute loss. But beneath that perception, a quieter process unfolds. Engineers return to their data. They refine their models. They redesign components. They test again. The system is rebuilt, not as it was, but as something informed by what has been learned. In this way, the destroyed rocket does not vanish entirely. Its influence persists. It becomes part of the next design, the next launch, the next attempt to reach beyond Earth. This continuity introduces a philosophical dimension to failure. If the knowledge gained from destruction enables future success, then the failure is not an endpoint, but a transition. The physical object is lost, but the information it generated continues to exist, shaping outcomes that have not yet occurred. It is a form of persistence that is not material, but informational. And in a universe governed by physical laws, information holds a unique status. It can be transferred, stored, transformed, but not easily erased. The patterns discovered in one context can be applied in another. The lessons learned from one failure can prevent countless others. This is how progress accumulates, not by avoiding error, but by encoding it into understanding. Yet, even with this perspective, there is something profoundly humbling about the scale of loss. A rocket represents an attempt to extend human presence beyond the confines of Earth. Its destruction is a reminder that this extension is neither simple nor guaranteed. It requires constant negotiation with forces that operate on scales far beyond everyday experience. The explosion is not just a technical event. It is a boundary marker, a point where human intention met the limits of current capability. And in that meeting, the universe responded with absolute clarity, not through words, but through the language of physics, a language that does not explain itself. It only acts. And in its action, it reveals with uncompromising precision what is possible and what is not. In the end, the explosion is not the story. It is the punctuation, a sudden, violent mark at the end of a sentence that began long before ignition and will continue long after the debris has settled. To see it only as loss is to misunderstand the scale of what is unfolding. Because spaceflight has never been about certainty. It has always been about approaching the edge of what is possible and asking whether the laws that govern reality will allow passage. Every rocket that rises from Earth is, in a sense, an argument made in fire. A claim that precision, knowledge, and persistence can momentarily align well enough to overcome gravity, atmosphere, and entropy. And sometimes, that argument fails. But the universe does not interpret failure as defeat. It does not assign meaning to destruction. It simply enforces consistency. Gravity continues to curve space-time with silent authority. Energy continues to transform according to immutable laws. Entropy continues its steady expansion, dispersing order into countless possible states. These processes are not obstacles in the emotional sense. They are the framework within which all existence unfolds. A rocket does not break those rules. It navigates them. And when it fails, it reveals them more clearly. The fireball that consumes a launch vehicle is not chaos in the absence of order. It is order expressed differently. The expansion of gases follows precise equations. The trajectories of debris obey conservation of momentum. The heat radiates according to thermodynamic principles. Even in destruction, the universe remains perfectly consistent. There is a strange clarity in that, because it means that failure is not random. It is lawful. It emerges from conditions that, if fully understood, would make the outcome predictable. The challenge is that complete understanding is always just beyond reach. There are always variables unaccounted for, interactions not fully modeled, complexities that exceed current comprehension. This gap between knowledge and reality is where human experience resides. We build models of the world, refine them, test them, and trust them. And most of the time, they work. They allow airplanes to fly, satellites to orbit, signals to cross the planet in fractions of a second. But at the edges, where conditions become extreme, those models are tested in ways that reveal their limitations. A rocket launch is one of those edges. It is a moment where theory meets the full intensity of reality. And in that meeting, there is no abstraction, only outcome. This is why the destruction of a $15 billion rocket feels so profound. It is not just the loss of an object, but the exposure of that gap. The realization that even at the highest levels of human capability, there are still boundaries that cannot be crossed without risk. And yet, the response to this realization is not retreat. It is continuation. Because embedded within the human drive to explore is an acceptance of this risk. Not as recklessness, but as necessity. To remain within the confines of certainty is to remain within the confines of what is already known. To expand knowledge requires stepping into regions where outcomes are not guaranteed. Space, by its very nature, demands this step. It offers no shortcuts, no gradual introduction. To reach orbit, to travel beyond Earth, to explore other worlds, requires confronting environments that are inherently hostile to human existence. Vacuum, radiation, extreme temperatures, vast distances. These are not challenges that can be softened. They must be met directly, with systems that operate at the limits of physics. And at those limits, failure is not an anomaly. It is part of the terrain. There is a deeper implication here, one that extends beyond engineering. It speaks to how humanity relates to the universe itself. On Earth, life has evolved within a narrow band of conditions. Temperature, pressure, atmospheric composition. These parameters define a zone where biological processes can exist. Outside this zone, survival becomes difficult or impossible without technological intervention. Space is almost entirely outside that zone. It is not designed for life. And yet, humanity persists in reaching toward it. This persistence is not driven by necessity in the immediate sense. It is not required for survival in the way that food or water is required. It is driven by something less tangible, but equally powerful. Curiosity, ambition, the desire to understand and to extend presence beyond current limits. A rocket embodies that desire. It is a bridge between environments that are fundamentally incompatible. And like any bridge built across a vast and unstable gap, it must contend with forces that threaten to tear it apart. Sometimes the bridge holds. Sometimes it collapses. But each attempt changes the landscape. Knowledge accumulates, techniques improve, materials evolve. The boundary between what is possible and what is not shifts, slowly but persistently. What was once impossible becomes difficult. What was once difficult becomes routine. This progression is not smooth. It is marked by moments of sudden failure and gradual improvement. The explosion, then, is part of a larger rhythm, a cycle of attempt, loss, understanding, and renewal. And within that cycle, there is a quiet resilience, not the kind that resists failure, but the kind that absorbs it, learns from it, and continues forward. The destroyed rocket does not represent the end of an effort, but a transformation within it. Its physical form is gone, but its influence persists in the data analyzed, the designs revised, the decisions informed by what occurred. In this way, the impact of the explosion extends far beyond the moment itself. It reaches into the future, shaping launches that have not yet happened, guiding systems that have not yet been built, altering trajectories that have not yet been calculated. This continuity is easy to overlook when confronted with the immediacy of loss. But it is essential to understanding the true nature of progress. Because progress is not defined by the absence of failure, it is defined by what is done with it. And in the context of spaceflight, what is done with failure is transformed into a deeper alignment with the laws that govern the universe. Each iteration brings human systems into closer agreement with physical reality. Each lesson reduces the gap between expectation and outcome. Over time, this alignment becomes precise enough to achieve what once seemed unattainable: orbit, interplanetary travel, observation of the cosmos at scales that were once unimaginable. All of these achievements are built on a foundation that includes failure as an integral component. This does not diminish the significance of loss. It reframes it. The $15 billion, the years of effort, the complexity of the machine, all of it matters. But it exists within a larger context, one where the ultimate measure is not the success or failure of a single launch, but the trajectory of understanding over time. And that trajectory is still rising, even when a rocket falls apart, even when fire consumes what was carefully constructed, even when the sky briefly holds the imprint of an ambition that did not reach its destination. Because the destination was never just orbit, it was understanding. And understanding, once gained, does not explode. It endures. It accumulates. It moves forward with every attempt, carrying with it the memory of what worked and what did not, and why. So the next rocket stands on a foundation that includes the one that was lost, not in material, but in knowledge, not in form, but in insight. And when it rises, it does so with a slightly greater alignment to the universe it is trying to enter, a slightly deeper understanding of the forces it must navigate, a slightly narrower gap between intention and reality. This is how humanity advances into a cosmos that offers no guarantees, not by avoiding failure, but by transforming it into a path forward. And in that transformation, the explosion is no longer just an end. It becomes part of something much larger, a continuous, unbroken attempt to reach beyond the limits of Earth, guided not by certainty, but by the relentless pursuit of understanding in a universe that never yields easily, but always responds with perfect, unchanging truth.